Hey, how's it going?
Hello, everyone. Welcome to the Embodied AI lecture series. Today, we're hosting Max Jaderberg. Max is a research scientist at DeepMind, where he leads the open-ended learning team. He completed his PhD in the VGG group at the University of Oxford with Andrew Zisserman and Andrea Vidaldi. Over the past few years, he's been involved in a bunch of exciting research projects, including AlphaStar, Unreal, and several works in population-based training, which is used extensively in this work today on scaling tasks and environments procedurally. So with that, it's a pleasure to welcome him today, and I'll hand it over to him.
Yeah, thanks a lot for having me here. I'm going to be going over this recent work that we released in June or July, open-ended learning, these are generally capable agents, which has been really the culmination of the past sort of year and a half, 2 years of work internally, which I'm really excited to present here. So, obviously, I'm coming from DeepMind, and this work is coming from DeepMind, and we're in this game of like trying to get to this point of AGI, right? This fable AGI, and the way we're thinking about it is actually there can be many, many different paths, research paths that can lead us to this point. And the work that I do and our open-ended learning team does is really focusing on one particular path, or like hypothesized path in this space. And maybe sort of central to our thesis is this idea of focusing on automatic generation of an ever-growing set of challenges for the agents. And to do that, having full control over the environment by the training algorithm. And crucially, without the need of human data. So maybe there'll be a tiny bit of human input, obviously us algorithm designers, but we won't be leaning heavily on collecting human trajectories and doing behavioral cloning. This is our sort of take on the path. And the work I'm going to present today is maybe the first tiny, minute step on this path, making what we're calling generally capable agents, a bit like a GPT-1 for RL. This, by the way, I don't know how you usually want to do questions and comments and things like that, whether it's better to jump in or wait to the end. Matt.
Are you all right if people just interrupt?
I'm perfectly fine with that. It's always more fun.
That works.
Cool. So yeah, as I said, the work I'm going to be presenting today is all based on this paper. It was really a fantastic team effort by a lot of people. You can see here, and I can't emphasize that enough. Okay, so the first part of this work is on the environment front. So we want these generally capable agents. What's the environment that we're going to be doing this in? As I said in the beginning, we want sort of full control over the environment, but there should be some properties that we care about. And the three main properties that we sort of focused on is vastness, smoothness, and having diversity in our environment. So when you think about vastness, this is just purely what are the number of tasks, the number of levels that can be generated. We don't want, if we're thinking about a general agent and we sort of like subscribe to the deep learning generalization hypothesis that with enough data and deep learning, you will start to get generalization, then we need tons and tons of data points. We're here in RL. A data point is a task, not just an observation, right? So we want, to be able to support potentially millions of different tasks. And the next point is smoothness. This is kind of related to vastness. Is if you have a vast space, it might well be smooth, but the smoothness says that, for every task that exists in this space, there's maybe another task which is epsilon away in terms of the types of challenges that it poses to the agent. Why is smoothness important? Because if we think about trying to create open-ended learning algorithms which automatically try and search and generate and move in the space of challenges and tasks in our environment, then having a smoothness property allows us to do some sort of optimization on the environment front. And then finally, we have this idea of diversity. It's all well and good having a million tasks, but if they're all, if they all look very, very similar to each other, and basically the agent has to do the same thing, but with tiny amounts of variation, that's not really going to cut it. So when we say diversity in tasks, we mean that actually like the challenges, the types of computation, the types of, maybe types of computation the agent has to do to solve these tasks is quite varied, at least in an optimal setting. Like when you think about the optimal policy for solving a task, it's very varied. What we'll see is actually that you can get behaviors that emerge which are very general and which apply to many tasks, even though they are very diverse in an optimal policy sense. Okay, so to sort of attack this, to try and get an environment like this, we sort of looking around. There wasn't anything existing, so we decided to sort of create our own, and we called it Xland. This is a multi-agent environment, and it's procedurally generated. It has procedurally generated worlds and procedurally generated goals. You can think of an instance of the environment being a combination of a physical world, so literally like everything around the agent that it can interact with in the sort of simulated physical world. The game that's being played, which is the set of player goals, so what the reward functions are for the agent. And then also, because this is a multi-agent environment, it also depends, the challenges faced by the agent depends heavily upon the policies of the co-players, right? You can imagine, playing the same game with an agent which acts very, very differently in response to what you're doing can completely change the challenge that's actually being presented to the agent. So this is sort of a high-level overview of the Xland space. We have, I don't know if you can see my mouse, but on the left we have this sort of galaxy of games, where here this is a UMAP embedding of the game space, colored by competitiveness and sized by balancedness. And each game here is something like Capture the Cube, where the blue agent wants the yellow cube to be on the white floor, but the red agent wants the yellow cube to be on the blue floor. And there's maybe this game has a certain level of competitiveness. This is probably quite a competitive game. But there are other games like hide and seek or match a sphere and a cube. As you can see, like this is our evaluation space. There's just a huge number of games in the space. And then each one of these games can be played on a world. As I said, these worlds are procedurally generated. I'll go into that a bit later, but you can see here some examples of the physical layouts that we have. So, and then we go into actually what a task looks like. This is sort of like a high-level sort of bird's eye view. You can see some of the floors. Here's a white floor. Here's a blue floor. Here's an orange ramp. If you zoom in a bit, you can see the red player. You can see the blue player. You can see the red player sort of holding a purple sphere. You can see a black pyramid. And then if you sort of look from the red player's perspective, this is the observation the red player would get. It's an RGB observation where you can see it's holding the purple sphere. So we call the topology, the world topology, the sort of layout of the floors. All of the physical stuff of the world. Then we have the game. So the game for this task that I'm depicting here is maybe the blue player has the goal, see red player or stand on the orange floor. And the red player has the goal, put purple sphere near black pyramid, right? And then if you look from the red player's observation, it only sees its goal, the red player's goal, which is put purple sphere near black pyramid. So hopefully that gives you an idea of what this environment space actually looks like and feels like for an agent and for an observer. So how do we create these how do we create these tasks? So first, world creation. As I said, there's three components: worlds, games, and then the other players that create worlds. So the world creation is procedure generated. It uses this algorithm called wave function collapse, which is really neat. And essentially, you can generate these topology height maps which have consistency rules, meaning that ramps will lead, will go between two floors, and you don't get any sort of weird artifacts. You basically get a tile set which is like different floors and different ramps and different elements. You define connectivity rules, like this thing can be connected next to that thing. You know, a ramp between floors 1 and 2 can't be connected to floor 5, for example. And then you have this wave function collapse algorithm, which you can kind of see in the bottom right, is doing this sort of, it sort of collapses a node, collapses a tile, and then propagates the constraints out, and does this over and over again. And then we have a system for spawning objects and for spawning players, essentially giving probability maps which have affinity to certain areas of the world, and then you get this full world, which we use Unity to simulate all this. Now, the nice thing about this method for generating worlds is that you can actually do sort of conditional generation. So conditioned on an existing world, you can do some sort of mutation and generate a new world. Here you can see sort of like an early prototype, sort of smoothly varying. Here's maybe a little bit more, this shows us a bit more clearly. You can see, this world, here's one step of mutation, and then another step of mutation down for a few different examples. So we have this sort of smoothness property in world space with this generator. And the first thing that this allows us to do is actually to do this process of world and agent co-evolution. So you might have heard of an algorithm called POET, which is doing something very similar. Like this is basically like inspired by that, where you're training an agent with a very simple goal of being near a yellow pyramid. At the same time, this agent is training on a distribution of worlds, and then on the other side you have this world evolution going on, where the fitness for world evolution is to keep the agent in a state of imperfection. So it can't quite solve the worlds all of the time, but it can solve them sometimes. So it's this like co-evolution process, which is mutating worlds as the agent gets better and starts to find the purple pyramid on like this simple distribution of worlds at the beginning of training. The worlds start to mutate and get harder, and the distribution gets richer and richer. And out of this process, we get a really interesting distribution of worlds, which is shaped by agent training. So you get like things coming out like long paths to get to the goal, or having to navigate around cliff edges, or worlds where there's many different directions you can go in, and the agent doesn't know what it is. So we use this process to generate a set of worlds that we and we take a snapshot of this process through training. So we have a whole collection of easy worlds all the way to really complex and harder worlds, at least from a navigation point of view.
Question.
So then, oh yeah.
So a couple of slides ago, you had mentioned that your worlds can be conditionally generated.
Yeah.
That slide seemed to suggest that they are conditioned on the previous world. But is my understanding correct? The conditioning is not just on the previous world, but it's also conditioned on the ability of a present agent. And so, because in order to go from easy to hard, isn't that conditional on what is hard for this particular agent?
Yeah, that's right. So the actual world generation process, so just a world in isolation, can be conditioned on an existing world, right?
Yes.
Now, when you put that in a work like this co-evolution process, where the fitness for evolving a new world, so and this could be, for example, in a rejection sense. So let's say in this new process, you have an agent at a certain point of training. Like the agent is mastering all the worlds that it's doing. So we take an existing world and we keep mutating it conditioned on the existing world until we find a new world that the agent starts to fail on. And then that gets a high fitness and gets put into the training set. So in this process, yes, the work, like through rejection sampling, the worlds are conditioned on agent behavior as well.
And I might be jumping a bit ahead, so please stop me if that's so. But is this a pure search process, in the sense that are you basically modifying your world, testing your agent, and then either accepting or rejecting it, or is there do you have a function that accepts the parameters of an agent, a world, and then outputs a new world? Like, is this a learned function? Or is this a purely search method?
This is purely search, like, you know, a dumb genetic algorithm. I would love it if we had a learned function, and you can probably imagine that we're working on that. Yeah.
Thank you.
Because
one more question. So what's the incentive for the agent to get better? I mean, the agent can remain dumb and it cannot like solve the problem, and instead that satisfies your criteria.
I should have said that the agent in this co-evolution process is being trained with RL to maximize reward, where reward is given when it hits the yellow pyramid. So the agent has no choice but to try and maximize return and get better at like finding the yellow pyramid. Yeah, does that make sense? Okay, so we look at the world properties. We have, you know, very diverse worlds. You can see some examples here. That's maybe obvious. There's a vast number of worlds. Again, that might be obvious, but we can quantitatively sort of estimate that. And then the really nice property of this world generator is that we can actually get smoothness in our world space, and we can sort of quantitatively show this smoothness by, you know, wiggling the world a bit, so wiggling the tiles a bit, and then defining metrics about what we care about these worlds. So, for example, there's something called resistance, which is sort of the shortest path between any pair of points. Actually, no, that's shortest path between any pair of points. And then there's resistance, which is like, what's the longest path between any pair of 2 points? These are sort of just simple graph metrics, and the graph is the sort of connectivity between the tiles, assuming a really simple agent movement model. So we have these metrics on the y-axis, and we have like varying the tiles, that, you know, moving a floor up and down, switching a ramp to a block, and we can see that actually as we wiggle in world space, we actually only get a small change in this metric space, and there's some nice theoretical results that give us a bound, which seems to be obeyed by the data. Cool. All right. So that's the world side. Then we're on to the game side. So our games are sort of represented in this way. Here's a game where player 0 has the objective C, player 0, player 1. And player 1 has the objective not C, player 0, player 1. So I don't know if you can guess what this game is, but this is actually the game of hide and seek. And in general, we can represent games in this sort of graph format, this like logical language, where you have predicates, things like see, touch, far, near, and then relations, which is sort of relations which act on objects, which is things like the players or the cubes and the spheres and things like that. So this hide and seek game would have this logical graph that looks like this. There's around 200 atomic predicates. I'm listing some out here, like near purple pyramid, purple sphere, see opponent, black sphere. So you know, see me, yellow pyramid. And you can combine these with and or. And we do this in just a canonical form called sum of products form, where you have like a set of options, And each option can be a combination, an AND combination of various of these predicates. So you could say, I want to see the black cube, have the black cube see the black pyramid, and be near the yellow cube, make the yellow cube be near the yellow pyramid, or just make me see the black cube. So you can have this sort of combination of different options. And again, so to actually create interesting games in this space, or trying to cover the space of these games, just uniformly sampling games from this space doesn't necessarily give us a good or interesting coverage of these games. So again, we start to look at what are some metrics of game space that we care about. And we have this idea of competitiveness. So competitiveness, one, means that like if you have two agents in your game, there's never a situation where the agents can be getting the same reward. And then you have balancedness, which is how much of the stuff does one player have to do, the other player has to do. So how equal are the and there's like how equal are the two sides of the game? So we can get everything from competitiveness 1, purely competitive, to competitiveness 0, which is like completely cooperative, and things in the middle, which could be, some options are competitive, some options are independent, some options are cooperative. And so there's a sampling strategy to sort of adjust the sampling of games so that we cover this competitiveness and balancedness space. And again, we can start to look at these properties of game space. We can see that they're very vast. Like, again, that's maybe not surprising because these are combinatorically combined. But there's also a diverse set of games. We can get obviously things like hide and seek, also things like capture the cube that I'm really happy about. Also simple cooperation games, or just like trying to find the yellow pyramids. So there's a very diverse set of games in this space. And crucially, again, we see that there's this game space is very smooth. Obviously, this is a discrete space, but it's more just like the world space was, but it's more, if we make one edit to the game, so you can think about edit distance, how much does, for example, the balance change? How much does the competitiveness change? How much does the exploration difficulty change? These properties of the game that we care about from an agent's perspective. And we can see that small changes in the game give small changes in these metrics. So that's really cool.
Question?
Yep.
If you want to design a competitive game, then the example you showed was essentially given a landscape or a world, one agent is moving objects around, in a sense, hiding something. And then the other agent has to go and, find those objects, in a sense, seeking. And this is given a landscape and given a, in a sense, task description, right? Which is your sequence of predicates. So this is competitive. And then a cooperative game is where both agents have to perform the same thing. So maybe they divide and conquer or somewhere. How do you get a smooth transition between cooperative and competitive?
Yeah, so an example is putting those two things together with an or statement. So the agent, like, you could choose, like, so now the game is one agent has the option hide the black cube or find the yellow pyramid, right? Or put the yellow pyramid next to the yellow sphere, okay? And then the other agent has the option, sorry, just to make this more explicit, the first agent has the option, don't let the other player see the black cube, right? Or it has the option, put the yellow pyramid next to the yellow sphere. And then if the other player has the objective, see the black cube, or put the yellow pyramid next to the yellow sphere, both agents have two options. One of these options if both agents choose one of the first options, then they play a purely competitive game. If they both choose the second option, then they play a purely cooperative game. But if one is choosing one and one is choosing the other, then they can both satisfy their goals independently, but they might mess each other up a bit. So there's this spectrum of competitiveness due to that.
Do you have the same rewards if you had a if you could change the rewards for these two two halves of the OR statement? That could also make it a smooth transition, right? You could say, well, I give you a reward of 3 if you win the competitive game, but a reward of 10 if you win the cooperative game. Then that allows you to be smooth.
Yeah, we only have binary rewards, so the reward is either 0 or 1 per step, per tick of the environment. But yeah, that would be another way. By the way, yeah, this competitiveness metric is only based on a game. It only looks at a game. It doesn't actually, take into account the actual policy that the agent is following, or the world that's being played on. It's just a rough sort of theoretical measure under like a very simple assumption of how agents behave. So think of it more like a game theoretic measure than actually in the instance of the world how competitive it is. But it's just something rough to ground our understanding of games. Okay, so we have this world space, game space, vast, diverse, smooth, and now we want to create these generally capable agents. But what do we even mean by generally capable, right? So I think the key takeaway is there isn't just one thing that makes something generally capable that we really care about. Obviously, we want agents that don't catastrophically fail, right? We want them to catastrophically fail on as few tasks as possible. So you give an agent a task and it just does absolutely nothing on it, spins around and looks up in the sky. We don't want that, right? So on the flip side, agents should be as competent on as many tasks as possible. Sure, like on our vast task space, we want agents to be competent, get some reward on as many of these tasks as possible. But how competent do we care about? Do we want superhuman experts? Well, the third sort of point is that we prefer broad ability over narrow competency. So rather than getting a superhuman agent, an optimal agent on a set of 100 excellent tasks out of the million that we produce, we would prefer an agent which is just okay, or even a little bit bad, but can get some reward on the whole spectrum of million. So the thing is that these points are kind of in conflict with each other, and so there isn't necessarily a single scalar that can push up all of these numbers at the same time. There's no way we can map this to a single scalar reward. So instead, we sort of look to more open-ended learning style methods. And when I say open-ended learning, I think one of the key sort of traits of an open-ended learning algorithm is this idea of incremental performance metric, right? That at the beginning of training, you don't know exactly what your scalar that you're trying to maximize is, but you move a little bit towards something you care about, and then you reassess your evaluation metric, and then create a new thing that you can move towards. So we have this idea of percentiles. So if you take a set of tasks, like here's 5 tasks on the bottom, these are evaluation tasks, some are hand authored, but these are tasks out of the XN space. And the first question is, how do you get how do you characterize the agent's performance across these tasks? Because these tasks are asking very different things of the agent, you can't just look at the agent's reward, its score on each task. Because if I say, okay, on this task where you have to stop a thing rolling, is a score of 100 good, right? Compared to this task where you have to put a block on top of the eye. You know, if an agent gets a score of 10 on here and a score of 100 on this task, like which task is the agent doing better on? Well, we can't compare these because the reward scale is completely different. The challenge is completely different, right? So the first thing to do is to normalize these scores. The first thing to do is normalize these scores by trying to get the best known score possible. And this best known score, ideally, in an ideal world, we could just get a bunch of people, a bunch of humans to play these tasks, set some human scores, and then we could normalize by human scores, a bit like you do in Atari. But because we have millions of tasks, we can't do this, right? So instead, we're going to take the best known score to us, to the algorithm at the point in time. So that will be, you know, the best known score that it's seen an agent doing, and use that to normalize the score. And this score is updated iteratively as the algorithm progresses. As training progresses, you want to change what your normalizers are because you've got a new definition of what's great on this task. Okay, so you first normalize the score by the best known score, and then you rank these tasks in order of increasing score. And what you can do then is sort of read off the percentile normalized score. So for example, percentile 50 is the median normalized score across this set of tasks. But we don't just care about the median, because we have this idea of, you know, median kind of pushes up, you know, almost this like expert level. But we also care about the agent, you know, catastrophically failing on some tasks. So it's not just the median we care about. It's not just like how many tasks the agent fails on, because actually, in reality, the agent is always going to fail on some tasks. So we look at lots of different percentiles in this space. So not just the median, but also, for example, percentile 0, which is the worst case, right, which is usually 0. There's usually always a task that the agent is completely failing on. Then there's an interesting example, which is what's the percentile that the agent fails on, that the agent stops completely failing on. So the first non-zero percentile is quite interesting. Okay, so that's sort of, yeah.
Quick question on this one. So do the agents, you know, when you go from task A to B to C, have the agents evolved, and does that affect the scores?
Sorry, I missed that.
So when you transition across tasks, the agents have evolved, or their you know, policies and other parameters, have those evolved? And if they have, does that affect the, like, do you revisit the scores?
No, we can think about, like, when we characterize an agent, we take a single agent. We can think about freezing the weights of that agent, then running that agent on all the evaluation tasks, getting the score of the agent on all of those evaluation tasks, normalizing those scores by the best known scores per task, then doing this ranking and reading off the percentile normalized scores. So, you know, the agent, like in this evaluation metric, you can think about a frozen agent evaluated on all these tasks. If that makes sense.
Thank you.
Okay, so on to the methods. So there's sort of a hierarchy of in this training process, and I guess so starting from the smallest timescale, the timescale of seconds, we are training these agents with reinforcement learning, and you know, we use this VMPO algorithm, and you know, on the order of seconds, the agent is getting experience in. We're running VMPO, doing local gradient updates to the neural networks. Then on the order of hours, oh yeah, and to be clear, when we're doing reinforcement learning, you know, now we have a task distribution that is being trained on. So there's like an instantaneous task distribution at this point in training. the agent is doing an RL update based on this distribution of tasks. Now, then we can think, okay, on the next level, how can we actually change that distribution of tasks to get the agent to become more capable? So RL is happening constantly at the order of seconds, always trying to maximize return, but on a distribution of tasks that's going to be changing over time. This distribution of tasks is changed to sort of, is evolved. The parameters of this task generation process is evolved to maximize these percentile scores for the agent. And we use PBT for that. So that's sort of on the order of hours in our training process. And then the final level is on the order of days. As we train agents and they get better under this percentile metric, they start to saturate. And we use a sort of a deep RL trick of stopping training and then reinitializing training from scratch. We're using distillation from the best agent that we found in the last period of training to distill and bootstrap the training of the next generation. And then we turn off distillation and let that agent train more. And we find that by doing this, we can actually get more performance out of the agent. But another benefit of this is that after we finish a generation of training, we can actually use that best agent to recompute our normalizer of percentiles. So as we were saying just before, we need to know what's the best score per task. At the end of training generation, we can take the best agent and say, hey, this is our oracle. This is the best thing we know about. Use this to recompute our best score per task. This gives us effectively a new evaluation metric every single generation. The other thing we can do is we can add that best agent into the set of co-players that the agent actually trains against in the next generation. So we're expanding the task space by adding new co-players per generation. So I hope that kind of makes sense. Just again, from the top, we train generations of agents. Each generation is composed of a population. Between each generation, we're taking the best agent and we're using that to bootstrap the next generation through distillation and add to the set of co-players. Within a generation, we have PBT acting on a population where each agent has its own task distribution, which is trying to maximize his reinforcement learning. And the task distribution is evolved using PBT based on these sort of percentile metrics. And an agent is considered better than another agent if it Pareto dominates the other agent across all percentiles. So I hope that makes sense.
Very quick question. I didn't quite get something about the scores. I mean, if the agent always performs poorly, that normalized score is always high, right? Is that right?
Yeah, there's some clipping. There's some edge case adjustments. So, for example, if the best score you know about on a task is 0, then you just don't include this task in the computation.
Yeah, but yeah. non-zero, but a very small value. Like in that case, then your normalized score will be very good.
Absolutely. So if you have a task where your previous best agent was getting 0.1, right, and now you have a new agent which is getting 10, that's an insanely high improvement, and the normalized score will be huge, right?
Yep.
But this is just one task of sort of thousands in the evaluation space, and so that task will be way down the sort of percentile 99 end. But what we really care about is looking at these like low percentiles, and so that new generation, that task will be out of play, and it's kind of it's solved by by what we care about in this generation, and so other tasks come in play and are focused more on in these low percentiles. So this process of like normalizing and re-ranking And it's also something that's done, I think, in Poet as well, like, you know, similar sort of idea, or extended Poet. It like really allows like different evaluation tasks to be dynamically, like the priority of them changes sort of based on this process.
I see. I thought the agent stops improving when it hits the maximum score. So which is, I think it's not a right assumption.
Max?
Yep.
Regarding the agent itself, how is the goal information conveyed to it?
I'm so glad you asked. On the next slide, I will show you that.
Thanks.
So the goal is like we use this sort of logical form of goal, and we use a graph network to process that logical form into a vector. I realize this diagram is actually probably more confusing, but maybe one of the key things to highlight is on the left we have the agent which looks at the RGB over here and has an LSTM and outputs a state. And you can see that there's no goal conditioning in this part of the agent. And actually only after the recurrent step do we condition on the goal. So the agent has to, like in its recurrent core, think about all possible goals that it could have to follow. And then we do this sort of multiplicative interaction with attention to condition on the goal. I'm not going to go into too much detail on this, but there's this sort of goal attention mechanism where we split the goal out into the different options. The agent has this internal value estimation of each of the options, and there's a softmax attention onto the hidden state of the LSTM based on which option has the highest value, and there's some sort of like internal consistency loss. I'll leave these details out for interest of time, but
just maybe one question about the goal then to understand, like, is the fact that it's encoded as a graph neural network, wouldn't that kind of make it so it kind of generalizes, it sort of helps generalization, I guess, and sort of an inductive bias towards generalizing to different kinds of propositions.
Absolutely.
Like language would, of course, make it harder to generalize, I guess, to new goals.
Language would make it a lot harder.
Also, is the goal conditioning purposefully designed to be after the recurrent steps so that the agent gets a more generalized understanding of its history and its environment?
Yes, exactly. You know, one thing is that it's like forced to keep a general sort of state of its environment around. The second is by having it after, you can actually change the goal that you're conditioning your agent on midway through the episode without destroying the recurrent state, without like the recurrent state suddenly becoming really out of distribution, out of training distribution. So this sort of modularity helps with, and it then helps with interpretability as well. You can say, okay, my agent's at this current state. If the agent has this goal, how does its internal belief change? If the agent has this other goal, how does the internal belief change? This means we can do this sort of like analysis post. So, yeah.
One other question. It seems like a lot of papers from DeepMind, you sort of use like MPO or VMPO for training. Yeah. Berkeley seems to use like soft critic, and a lot of others seem to use PPO. Is there any convincing reason to use VMPO here, or does it not matter that much and the task is ultimately more important?
It doesn't matter that much. Is probably the answer. I actually like I was chatting to Igor Mordach, I don't know if you know, who used to be at OpenAI, now Google Brain. You know, hey, like at OpenAI, there's a lot of PPO, right? Should we be using PPO? And it's just much of a muchness. And I think each lab and each institution, each lab has a well-tuned, you know, actor-critic algorithm and framework around that. And at least in my experience, it doesn't make too much difference. We did see a substantial change going from, for example, Impala sort of like pure vtrace to VMPO in other projects, but yeah, I think like amongst these actor-critic algorithms which automatically adjust the sort of some sort of temperature or expiration parameter, yeah, at least my my rough read is they're fairly similar.
Makes sense. Thanks.
I'm going to move on a little bit to training. Here in this figure, this is actually like the whole training process of the paper like displayed. Each of these columns is a different generation. We train 5 generations in total. And the graphs are different metrics. We have percentile 50, which is the median evaluation score. But then we have percentile 10, which is the 10th percentile, obviously. The hand-authored reward, which is we have this special held out hand-authored set of levels where we're measuring like just mean reward on. And then we have this measure participation, which is what percentage of the tasks does the agent get at least one reward in? So you can think of this as how not catastrophically failing an agent is doing. And you can see that as these generations progress, we take the best agent, we use it to bootstrap the next generation, and the next generation starts to exceed, at least on some of these metrics, the performance of the previous generation. There's a few ablations, which I'll probably skip over in the interest of time, but the main thing is this idea of dynamic task generation, changing the distribution of tasks the agent is training on, really does allow this learning to occur. And the nice thing is that here in this diagram, we're looking at the percentiles as they're changing through the final generation of learning. This is on an automatically generated evaluation set. And the cool thing is that this metric of percentiles, we can see the percentiles seem to grow through training, which is great. But this the actual agent, when we look at the zero-shot generalization on hand-authored tasks, we see that this is also generally growing. And so actually maximizing percentiles across an automatically generated evaluation set translates to expected return getting better on these like interesting hand-authored tasks we devise, which are more out of distribution to the training levels. Okay, just videos now, I promise. Here's some examples of tasks the agents are doing, and this is all at test time now from the trained agent. All of these tasks are completely held out. They're never seen before during training, both the games and the world. So we have agents playing Tag Fiesta. They have to keep, in Tag Fiesta, they have to keep all the other agents off from touching all of the other floors. So they end up using their tag gadget for that. We have Capture the Cube, where you score a reward for getting the cube onto your base floor when your cube is there. We have the game of hide and seek, of course, where one agent is trying to run away and not be seen by the other agent. And things like King of the Hill, where I'll look at these in a bit more detail. So here's one called Stop Roll. This is one of my favorites. So I'll just pause this here. You have a world that looks like this. The agent gets reward when the purple sphere up here is not touching the red floor and the player is not holding the purple sphere. So you have to get the purple sphere to not touch the red floor without holding it. And there's obviously, it starts up here on this world, which has a big slope. So and this is all zero shots performance. The agent like holds it, moves up, and starts sort of using its body to block the sphere from rolling down a little bit. And as things go on a little bit more, the agent sometimes finds these solutions where it actually traps the sphere between its body and the wall, or does other things like ends up putting the sphere on these plank objects, on these wall objects. We see the same agent exhibiting multiple behaviors. So in this task, the blue agent has to try and stop the red agent from touching the red floor. There's two ways you can do that. One way is running around. Here, this is a test time evaluation task, so the red agent isn't controlled by anything. It's just staying still. So in one episode, the agent goes around, tags the red agent, stops it, and then actually like starts lifting it up, a bit like Simba, so it stops touching the red floor. In another episode, it just stays where it spawns and just repeatedly tags the red agent. This is the same agent, the same network, just a different random seed. We also have examples of agents using tools. So in this example, the agents have to get to this purple pyramid, which is, there's no way up. There's no topology that would go up. This is actually out of distribution. This would never happen in training. But the agents are sort of throwing stuff about, experimenting, and end up, creating a ramp, freezing it in place, and going up and getting the pyramid. Episode to episode, we see different forms of behavior emerging, like different types of this behavior, different ways of creating this ramp. This doesn't always happen, but it's interesting to see that there's lots of different ways that the agents end up getting this pyramid. It's really hard to talk about. Yeah.
So when you say it's like tool use, that kind of implies it's a sort of systematic solution. Do you think that is it sort of randomly throwing things around and then seeing when something works, or do you think there's something more systematic and like knowing that ramps can be used for, like how much do you say it's systematic versus like it knows to? It seems like it knows to experiment quite well. Like it'll move things around in the environment.
Exactly. I really don't want to claim anything about intentionality here, because I really think like I've watched hundreds of videos and the agents don't know what they're doing in this scenario, right? But they have learned this meta policy of throwing things around, interacting with the objects of interest, right? And they do recognize when an affordance changes, when like a path opens up that wasn't there before. Here's another example of this. I think this really shows this. This is near, not near, where the agent has to get a certain spatial arrangement of these cubes next to each other. So two are near each other, but a certain pair are not near each other. And the agent clearly knows to interact with these cubes, that the goal is something to do with these cubes, that something about the arrangement, but doesn't know what the arrangement is, and just keeps randomly sort of like popping them down next to each other and throwing them about, always next to each other, but like kind of in a random order. Then it starts getting reward. And at the point it's getting reward, it can see that actually, oh, this is a rewarding state. I'm going to stop messing with these cubes now. So there's this behavior of experiment, and if I recognize that I'm in a rewarding state, stop experimenting. And in this example, we see this over and over again, and it's really clear to see, which is really cool. It's this this is the sort of generally capable behavior that I think we should be looking to get out, where it's a meta policy which works in a huge number of tasks. Just try things out, and if you see something that's correct, then stop trying things out.
Yeah. Oh yeah. So given that like in a lot of these cases, you see sort of like multiple emergent behaviors, how are you verifying like what is desirable behavior for like a particular task? Because you can imagine like specification gaming kinds of cases where it's kind of hard across like a very large distribution of like tasks. It's getting reward in ways that, you know, are not conductive to this sort of overarching goal of like being generally capable. Like this was like a notorious thing back in like Atari days where it was just like exploiting a glitch in the engine kind of thing.
Yeah, exactly. I mean, that's the problem when you have just a single game that you're training on and that you're evaluating on. The point about having this like massive wide space is that, yes, there will be games in this space which are, one, impossible because of bugs in our generation code and verification code, two, that are going to be trivially easy, three, that are going to be exploitable, but hopefully the majority won't be like that. And at least there are enough, like even if like 10% or even, you know, or 20% of levels are impossible, exploitable, or trivially easy, even if 90% are like that, we can just generate more and more and get enough that we're actually focusing training, because training automatically focuses on these lower percentile levels, right?
But it doesn't have to be the case that like the agent is only like highly performing on like an exploitable like level, right? So how separable is this in terms of the percentiles into like sort of like an exploitable versus non-exploitable? Because it could perform highly, like really well on like a non-exploitable level.
Yeah.
Yeah.
It doesn't from the evaluation metrics side, like we don't really care about the individual case, I guess, is the point. Like, yes, it might, like, it's going to, like, the percentile metric is going to conflate two things, like the level which an agent nails and a level which an agent exploits are both going to be super high percentile. But at that point, we don't care about either of those. One of them because it's exploitable, and another because it's already been solved, right? So I think just like this like shoving away like high performing levels and just like focusing on these, you know, not performing very well levels, sort of mitigates this automatically. But yeah, it's a good point. Like, if too much of this exploitability exists in the evaluation space, this all breaks down. So
yeah, yeah, no, it makes sense. It's better than having like a monolithic sort of environment.
Yeah, I realize I'm out of time. So the final thing I'll just end with is that all the results I've been showing so far are zero shot. All the results I've been showing is zero shot, but we can fine tune these agents to these levels and they actually do very well. So we can think of this process as almost like a pre-training process to get to okay behavior. And then if we really care about a particular task, we can fine tune. Okay, I'll stop there since we're out of time. Yeah, thanks a lot for listening. I hope this was interesting.
Thank you for coming. It's been a pleasure.
Thank you so much. Thank you for the great presentation. And thank you for staying after 5 p.m. your time for the talk. We appreciate it.
No worries. It's great to be invited. All right, have a good Friday.
Thank you.